Okay, let's look at a problem now that involves both dependent and independent sources. And the steps that we were using before were sort of deviating from a formal method, and now we're going to take a look at what that formal method should be. Oops. So what we'll do is, and this method will actually give us both Thevenin and Norton. So even though I didn't say that, that's what we'll be able to get. First, we identify the load, okay, and that's what I've done here. Identified the load. Then we'll remove the load and redraw the circuit twice. Once we'll draw it as a short circuit across where the load was, and then we'll draw it as an open circuit where the load was. And we'll solve for the open circuit voltage and the short circuit current. This is when we have at least one independent source and one dependent source. This is the only way to calculate R Thevenin. Okay, we'll do the ratio of the voltage that we found to the current that we find. And then we can finally use either VOC and R Thevenin or ISC and R Thevenin to calculate the Thevenin or Norton equivalent, and then we can solve the problem. Okay, so the first thing we do, we identify the load. Now we will redraw the circuit, and we'll draw it, I'll start with it as open, and we need to solve for VOC. So there's no avoiding, in this case, solving for VA first, because VOC is directly tied to VA. So we'll have to remind ourselves of the things that we know about these open branches of in a circuit. This has a voltage, but it does not have a current because it's not in a loop. Okay, which means that this voltage source, which is driving a current, is driving it only through this loop. So that means that we can solve for VA by doing voltage division here. Okay, recognizing that all the current's flowing here and all the current is flowing through there. So voltage division will tell us that VA equals 12 times 4 over 6, which is 2/3. So that equals 8 volts. Okay, so now we know VA. And now we can employ sort of any method that we want to solve for VOC, because there's really nothing that we can't solve at this point. We could do KCL around this loop and then KCL around this loop. We could try doing nodal analysis. But I always look for the simplest possible way, and so don't forget to look for loops that are not just the smallest loops. For instance, what if I did the loop around the entire outside, including across VOC? Well, then I would have source, a voltage that's known, a voltage that's known, and only one unknown. Okay, so that's a done deal right there. Let's try it. Minus 12, I'm starting from down here. We're going through the negative terminal. Then we go through the positive VA. We now know that VA is 8 volts, so plus 8 volts. Then we go through the positive of this positive terminal of this source, and that's 2 times VA, 16. And then finally we go through the positive terminal of VOC. That equals 0. And so we get 12 over here minus 24, and so VOC equals minus 12 volts. Okay. Now, something to notice when you get a negative voltage or negative current, whichever one you do first, if you get a negative value for this, then the next one has to be negative. Why? Because the current, resistance is never negative. So V over I has to be a positive number. Okay, so that can be a sanity check for us later on. All right, now let's redraw the circuit, short it out. And now we need to solve for VA once again. So let's see how we can do that this time. Well, I could do KVL, but the current is not all flowing through here now. So I'd have to calculate this current. But once again, I can go around the outside of the loop, and I'll have one equation and one unknown, right? I know this. This is VA, and that's 2VA. So let's do that. We'll do KCL outside, KVL outside. So we'll start down here, negative 12 plus VA plus 2VA. And then that's it. We're back where we started. So that equals 0. So then VA equals 12 over 3, and therefore VA equals 4 volts. Okay, so now I know VA here, which means I can calculate this current. So we need to figure out what ISC is. We could try doing some KVL equations. I think that it would probably be not a bad idea to look at this node right here. If we can calculate this current coming in, and we already know it, and then calculate this current coming in, or I guess we'd say it's going out, then we can calculate ISC. So let's try doing a mesh right here. And we might have to do a mesh right here as well. Okay, so I'll start here, and I get minus 12. So let me label this KVL at 1. So we'll start down in the lower left-hand corner. So we get negative 12 plus VA, which is 4 volts, plus we're calling the positive terminal here, so plus 2K times I1 minus I2, which is ISC. So I'll just rewrite that immediately as ISC. And this equals 0. Okay, let's move this over to the other side and simplify this equation. So we get 2K times I1 minus 2K ISC is equal to minus 8, so equals plus 8. Okay. And what is I1? Well, we know what I1 is, right? Because we have a voltage and we have a resistor here. So if VA is 4 and we have a 4K resistor, we have 1 milliamp. So we also have the equation that says I1 equals 1 milliamp. So we can now plug in for I1, and then we can solve for ISC. So this is 2k times 1m, so that's 2 minus 2k ISC equals 8. And we'll bring the 2 over to be negative 6, and then we'll divide by, we'll bring the 2 over to be 6, and then we'll divide by 2k, by negative 2k, and find that ISC equals negative 3 milliamps. And remember our sanity check, the value is negative. So we can feel confident, fairly confident, that we have the question right, because that's going to give us a positive resistance. So VOC is negative 12, therefore R Thevenin equals VOC over ISC, which equals negative 12 over negative 3, 3m. Okay, and that then equals 4k for the resistance. And so now we're free to draw Thevenin or Norton, because look, we have ISC and we have R Thevenin. So we could draw it like this, or we could draw it like this. Oops. $4K here, 4K here. Remember, our current is actually negative and our voltage is negative. So that means that these have a flipped polarity. So I didn't draw this correctly. This should be minus plus like this, and then this would be pointing downwards. Okay, and this would be then 3m, and this is, what was it again, 12? Yeah, 12. Okay, and then you can plug in for your value here. What was the original? It was a 4K resistor here is our load. Okay, so this would be 4K, or this would be 4K. And then you can solve that problem. And I'll leave that up to you guys for that one. Voltage division here, because we're being asked to find the voltage, V0. Voltage division there in one step, you're done. Or you could do current division here and then back solve for the voltage. Okay? Good luck.